Hi, my name is Eitan, and I'm presenting our talk on simple tests of quantumness, also certified qubits. So what is a test of quantumness? A test of quantumness is an experiment which demonstrates the supremacy of quantum computers over classical supercomputers. In the image to the right, you can see the Google Sycamore chip, which performed quantum circuit sampling. This test has an exponential running time for verification, and we focus on proofs of quantumness which are efficiently verifiable by classical computers. So an example of a proof of quantumness which is efficient to verify is performing Shor's algorithm. A verifier generates two primes P and Q, and she sends N, which is the product of P and Q, to the prover. The prover needs to return P and Q. This shouldn't be a classical prover shouldn't be able to do this, but a quantum prover should be able to do this. Problem with this sort of protocol is that it is hard to implement on noisy intermediate scale quantum computers. Some previous works, Berkersky, Cristiano, Mahadev, Vazirani, and Vidic showed an efficient test of quantumness based on LWE with an adaptive hardcore bit assumption. This additional assumption meant that they needed an aggressive setting of parameters for LWE, which hampers practical implementation. Recently, Yamakawa and Zandri showed protocols of quantumness in the random oracle model. Additionally, there have been two proposals in the standard model with less computational assumptions than the previous proofs of quantumness by Kanomoku, Meyer, Choi, Vazirani, and Yao, and by Kalai, Lombardi, Vaikuntanathan, and Yang. But now that we have these proofs of quantumness, could we use these proofs of quantumness for other tasks? For example, could we delegate computations to quantum computers? Could we make them generate certifiable randomness? A very useful block for these sorts of protocols is the qubit certification protocol. And what do we mean by qubit certification? What does it mean for a quantum computer to have a qubit? We give an operational view of qubits. In our definition, a qubit is a triplet psi, x, and z. Psi is a quantum state that the prover has, and x and z are two binary observables which approximately anti-commute on psi. The classical verifier needs to verify that the quantum prover has this state psi, and also that he has these two binary measurements which approximately anti-commute on psi. And the question that we are interested in answering is whether we could use existing proofs of quantumness as tests of qubits. And our answer is yes. Okay, so we show that for a specific class of protocols, there is a quantum soundness barrier against quantum cheating provers. This is different from the bounds that were known for classical provers. We also show that the provers which approach the quantum soundness barrier must perform anti-commuting measurements. And this gives us a qubit test. We would like to comment that Natarajan and Zhang show related results for the KLVY22 protocol, and they also show how it can be used to get a protocol for delegation of quantum computers for quantum computation. These results are incomparable because we show our results for a broad set of protocols, and they get the full protocol of classical delegation of quantum computations. So here's our protocol template. In the first phase, the prover and the verifier interact, and at the end of the interaction, the verifier chooses whether to reject, accept, or continue. At the end of the first phase, the verifier has some random coins, the transcript of the protocol, and the prover holds some quantum state. If she chooses to continue, then they engage in the second phase of the protocol, in which she sends some challenge to the prover, and the prover replies with some response. And if the response bit corresponds to some pre-known computation, which depends on the randomness and the transcript, then she is going to accept. Just For you to remember, there is this challenge, which is M, and the response, which is B. To prove soundness for classical provers, usually we use a rewinding argument. We first prove that it is hard to compute the parity of both challenges, C hat 0 times C hat 1 with some noticeable advantage. And we show that a classical adversary which achieves a 3/4 plus epsilon success probability can use a rewinding strategy to compute the parity with some noticeable advantage. The problem is that in the quantum world, quantum computers cannot perform rewinding because once the state has been collapsed, the quantum computer cannot revert it back to its previous state. But still, could the quantum computer compute the parity with some noticeable advantage? To answer this question, we model our quantum computers using a set of projective measurements, which the quantum computer performs on its state psi of trance. And these measurements are denoted pi bm, where B, I'll remind you, is the response bit and M is the challenge bit. Here's our parity algorithm. We first execute algorithm 1, which executes the first phase of the protocol, aka the setup protocol, to obtain a transcript and a quantum state, and also a flag. Then we execute algorithm 2 on the state, which performs the first set of measurements corresponding to the case that the challenge bit is 0. And on this state, once it has already been measured, we also perform the measurement using the set of measurements corresponding to the case that the challenge bit is 1. Finally, we return the XOR of B0 and B1. To prove soundness for quantum computers, we first need to show, very analogously to the classical setting, we need to show that it is quantum hard to compute the parity of both challenges. Then, as a quantum analog, what we show is that to what we saw in the classical setting, we show that the quantum adversary that achieves a success probability of cosine pi over 8 squared plus epsilon must be able to compute Q1 is pi of C hat 1, 1. These are the measurements corresponding to the correct measurement results. And we show that these two measurements must be close to anti-commuting.
Hi, Eitan. Just so you know, we lost about 30 seconds or a minute there. The screen froze. So if you want to rewind a little bit, that'd be great.
Yeah, sure. Here? Okay.
Let's see. Maybe go back one more. Yeah.
Okay. So analogously to the classical setting, we prove that to prove that soundness for quantum provers, you first need to show that computing the parity of both challenges is quantum hard. And as analogously to the classical setting, we show that a quantum adversary that achieves a success probability of cosine pi over 8 squared plus some epsilon must be able to compute the parities. Just to recap what I said, parity hardness implies soundness. In particular, in the classical setting, parity hardness implies at most 75% success probability, and in the quantum setting, parity hardness implies at most cosine pi over 8 squared, which is approximately 85% success probability. This quantum soundness result also gives us a qubit test. We prove that a prover which approaches the quantum soundness barrier must possess two measurements, Q0 and Q1, which are pi of C hat 0, 0 and pi of C hat 1, 1. And these two measurements must be close to anti-commuting on its quantum states. So to demonstrate an example protocol which fits our template, let's look at the a modified version, a simplified version of the KCVY protocol. To explain how the protocol works, I need to first define a cryptographic primitive, which is called trapdoor claw-free functions. These are keyed functions with a trapdoor T. These functions are 2 to 1 in the sense that every y corresponds to 2 x's. So it looks like this sort of claw. Now, these trapdoor claw-free functions have this property that is hard in the quantum sense to find claws. These are two inputs, x0 and x1, which have the same output value. But given a trapdoor, it is easy to invert f. We require an additional property that it is efficient to generate superpositions over the input space of the trapdoor claw-free function. Moreover, that it is efficient to distinguish between x's, which are x0s, and x's, which are x1s. That is, given a value x, we can tell whether it is the first value of the claw or the second. All known trapdoor claw-free functions have this property, at least the ones that I know of. Okay, so to explain how this protocol works, I will explain it from the perspective of the honest prover. In phase 1, the verifier generates a key and a trapdoor to the trapdoor claw-free function. Then she sends the key to the prover. He generates a superposition. He measures the Y register, collapsing the superposition to some claw, and he sends Y to the verifier. He can now throw away Y as it is not used anymore in the protocol. Then the verifier is going to generate these two n-bit strings R0 and R1, with which he's going to perform an inner product. He's first going to compute an ancilla bit using this additional property I talked about that he can distinguish between x0s and x1s. Then using this ancilla bit, he's going to perform a conditional multiplication operation. So he's going to multiply x0 by r0 and x1 by r1. And finally, he's going to anti-commute the ancilla using, again, this property that I talked about. Then he's going to perform a Hadamard on the X register, and he's going to measure this X register, and he's going to send this D, which is the result of the Hadamard measurement to the verifier. Then to reach this stage, phase 2, in which the verifier sends a challenge to the prover, and the honest prover decides to perform a measurement based on the challenge bit. So if the challenge bit is 0, he's going to perform a measurement in this basis, which is the pi over 8, 5 pi over 8 basis. And if m equals 1, he's going to perform a measurement in the minus pi over 8, 3 pi over 8. So this is very similar to the measurement basis in the CHSH game. Finally, he's going to send B, the outcome of the measurement, to the verifier. Just to recap, in the first phase, the verifier sends the key to the prover, and the prover generates a claw and measures Y. Then the verifier sends R0 and R1, which are two n-bit strings, with which he multiplies x0 and x1 correspondingly, and he performs a Hadamard computation. And finally, he's going to send this D, which is the result of the Hadamard computation. Then they reach phase 2 of the protocol, in which the verifier is going to send M, which is the challenge bit, and the prover is going to respond with B, which is the response bit. The verifier is going to accept B if it is the expected measurement outcome. If you suppose that the prover follows the honest prover behavior. Because she has the trapdoor T, she can find x0 and x1. So she knows precisely what is the superposition of the claw, and she knows what the expected measurement outcome. So she's going to accept B if it corresponds to this expected measurement outcome. Now, we show that quantum provers can, any quantum prover cannot get more than 85% success probability. It is easy to see that if she knows the parity, if she knows the parity of the expected measurement outcomes, then she can compute R dot C0 concatenated with C1, where R is the concatenation of R0 and R1. And using Goldreich-Levin, she can find the claw. Indeed, the post-quantum trapdoor claw-free function assumptions lead to the hardness of computing the parity, and this protocol complies with our template. So here are some open questions which are left unanswered. We would like to know how we could generalize our approach to test of quantumness as in the BCMVV18 paper and the ones that operate in the random oracle model. Another open question is whether we could extend this hierarchy of verifiable protocols and what is the minimal basis for achieving these capabilities. As you can see in the diagram, proofs of quantumness based on non-rebinding give us qubit certification, which in turn lead to certifiable randomness and classical delegation of quantum computation. Could we extend this? Is there something even more basic for achieving these capabilities? Thank you for listening.
Questions for the speaker?
Great. Thank you. Thank you for the opportunity. Oh.
Hi, this is Paul Kwiat calling or speaking, questioning.
Yes.
The example that you gave in terms of testing quantumness is based on sort of local operations, I guess I would say, everything happening together. But of course, there are other tests of quantumness involving non-locality, so-called Bell inequality tests, where you have separated systems and you're able to incorporate as well sort of relativistic constraints. And I guess I'm just trying to understand the role of those where you don't have these complicated protocols going back and forth. You could imagine asking the person to sort of split their system into two pieces that are sufficiently far apart and then being able to demonstrate a legitimate violation of a Bell inequality. And I feel like some of the measurements you're making are sort of similar to those anyway. I just wonder if you could comment on that.
So we use the trapdoor claw-free function basically to remove this spatial assumption. So basically, there's a lot of ways of taking these known local games and compiling them to local games. And this is just one way to do it.
Okay, other questions?
I have a question. So I guess the soundness against classical cheating provers, which I guess they're all cheating, you can amplify that with the proof of quantumness, right? To get, a soundness gap that's 1 minus negligible. So can I also do amplification in this setting? And, what do I get? Can I possibly get like a qubit that's nearly perfect or something like that?
Well, basically, we don't, I don't know, we didn't actually make it into a full protocol for qubit certification, but we can show that there's another work which was published right after a paper. These are like people that work with us, and they showed how you can use amplification. So if a quantum prover approaches this soundness barrier that is like approximately cosine of pi over 8 squared, then you can get basically perfect qubits. But this requires some like additional work, but it complies with our framework.
Other questions? Okay, well, let's thank the speaker again.